Steinhauer here, welcome back. We've used this term before, but let's define it for real now. A singularity is defined to be a point source, right? If an object can no longer be supported by any known means, it must then collapse down into a single point with zero radius, and we call that thing a singularity. One more thing I want to talk about these black holes, and an interesting feature that happens at the surface is called gravitational redshift. So when you've got a normal mass, let's say you're throwing a ball up in the Earth's gravity, what happens? Well, you throw it up with some initial velocity, and that ball has some kinetic energy that's associated with that motion. And as the ball moves upwards, that kinetic energy, the velocity slows down and the kinetic energy goes away. And that kinetic energy has to go somewhere. It can't just be destroyed. It goes into potential energy, right? The higher an object is in the atmosphere or above the Earth, the higher its potential energy. And so as it moves up and slows down, that gravitational energy, the kinetic energy, is turned into gravitational potential energy until the object turns around and all of the kinetic energy is gone and all of it has been converted into potential energy. What happens then? It starts accelerating downwards and increasing and converting its gravitational potential energy back into kinetic energy. And so the object will then move back. A similar thing has to happen with light. As light leaves a massive gravitational object, it has to escape the potential well of that object. It's trapped down in the space-time at the bottom of that hill, the bottom of that pit of space-time. And so it must also, because it's gaining potential energy as it moves out, lose energy as it moves out. It, though, can't lose kinetic energy in the same way that a ball can, because it can't slow down. So how else can a photon lose energy? There's only one way that a photon can lose energy. Remember our energy of a photon equation that we wrote down earlier in the semester. It was E equals h times c divided by lambda, where h and c are both constants. H is the Planck's constant and c is the speed of light, and lambda is the wavelength of the photon, right? So energy is inversely proportional to wavelength. So these two being constant, if we need the energy to go down, which we do, the wavelength must go up. And that's what happens. Light that's emitted near the surface of a black hole will lose energy as it moves away from the black hole and shift towards a longer wavelength, which is a redshift. And so that's what we call gravitational redshift. Light that is emitted near a black hole will look much redder than it should because it's lost energy as it moves away from the black hole. Okay, here's a video where we examine exactly what goes on as an object approaches the black hole.
You've got two rockets that are orbiting the black hole. Let's just play this and let time run forward and see what happens. One of these objects, I think it's going to be this one when it gets to the bottom, is going to turn on its jets and fall into the black hole. Let me stop it here. If nobody turns on their jets, these guys are just happy orbiting this black hole. Nothing unusual happens, other than somebody who's way out here will see their clocks running a little bit slower. This rocket wants to fall into the black hole. What's it going to have to do when it gets down here? It's going to have to fire its rocket. And which direction is it going to fire its rockets to get to the black hole? You might think it would fire it down to get to the black hole, but that's not the actual best way to do it. It's going to fire it in this direction. All it has to do is slow itself down. If it can stop its orbital velocity, it will fall directly into the black hole. And so that means firing in a direction opposite of the direction it's moving is the most efficient way to get into the black hole, interestingly. All right, this isn't exactly how it's going to work, but it's going to start falling into the black hole now, and you're going to see two things happen. One is these clocks are no longer going to be synchronized and agree with one another. As this guy gets closer and closer to the event horizon, time is going to run slower and slower. And the other thing that's going to happen is it's going to get redder and redder. Time is running slower and slower. It's getting redder and redder. Time is running slower and slower. It's getting redder and redder. Time is running slower and slower. Slower and slower. Slower and slower. Slower. And that's pretty much it. this rocket ship will get slower and slower and slower and slower. And this rocket ship that's still outside will never actually see the probe that it sent into the black hole cross the event horizon. Time gets slow, so slow at the event horizon surface that it's basically not running at all. So what will happen, you'll just see this thing get slower and slower and slower and redder and kind of fade away into nothingness.
Okay, so what would happen if you were to actually jump into a black hole? Well, bad things. There's a thing called a tidal force. And a tidal force is simply the difference in gravity that an object feels on one side of it as opposed to the other side of it. And when you're near, say, a 3 solar mass black hole, this difference in force becomes very intense, enough to stretch you out, right? So this may seem a little counterintuitive because all of the forces are pointing down, right? But this astronaut is feeling a force of gravity down on his or her head. They're also feeling a force down on the feet, but this force is going to be a lot stronger than the force at their head. And this is going to, even though both of them point down, cause this astronaut to get stretched out as they fall towards the event horizon. And this force becomes so small, so large for these small-sized black holes that no known substance can withstand it. Astronauts, objects, all get ripped apart as they approach an event horizon. And it's even worse than that, because if you imagine what the force of gravity that this point on the astronaut is feeling, it points a little bit in this direction just because the source of that gravity is so close. And this one points a little bit in this direction. And so not only is this astronaut getting stretched in one direction, the astronaut is getting squeezed in the other direction as those two arrows come together. And so all of this is bad news for an astronaut. And in a small black hole like a 3 solar mass black hole, this becomes lethal way before you get to the event horizon. In fact, for a black hole like this, individual molecules can't even survive this force. They get ripped apart as they fall towards the event horizon. There's a technical term for this. It's one of my favorite words. It's called spaghettification. Let me just write that down. You can impress your friends with that one. So interestingly, if you are interested in jumping into a black hole and surviving, these tidal forces get weaker for larger black holes. Yes, the mass gets larger, but the event horizon gets pushed out far enough that the more massive you have a black hole, the smaller the tidal forces at the event horizon are. And by the time you get to a black hole that's millions or billions of solar masses, they are now weak enough that you could survive and actually jump into a black hole through the surface of a black hole and not be immediately ripped apart. So what does happen to you as you jump into a black hole? So if you're watching someone else fall into a black hole, let's say you send a probe into a black hole, that probe, as we know, clocks on that probe, and time for that probe will get slower and slower and slower, and the object will get redder and redder and redder as the gravitational redshift takes over. And in fact, it will get slower and slower as it approaches the event horizon. You will never see that object cross the event horizon because the time becomes so slow. And in fact, what will happen, you'll just see this thing sort of fade out and become redder and dimmer and fade out altogether over time. You'll never actually see it go through and cross the event horizon. Now, what happens if you're jumping into this black hole? Well, again, time runs normally for you wherever you are. So for you, it's not that your clocks will run slow, it's that everybody else's clocks behind you will seem to be running faster. And the closer you get to the event horizon of that black hole, the faster the clocks behind you seem to move. And in fact, as you cross the event horizon, you'll see the entire universe behind you age to infinity. So if you want to know what the end of the universe is going to be like, you can do that. You just need to jump into a black hole. Time travel is possible, but it's only possible in the forward direction. You can't go backwards. Now, of course, once you're inside the black hole, you may see many wonderful things in there, but you're never going to be able to communicate them to anybody outside the black hole. One, you'll never be able to leave the black hole because not even light can escape. And two, you'll never be able to signal anybody out behind you. One, because the universe is aged to infinity behind you. And two, because no information, no light, no nothing can leave the inside of that black hole. And so you won't be able to tell anybody about the amazing things you're seeing in there. And eventually, once you're inside the black hole, you have an inevitable journey to the center of that black hole, where eventually the tidal forces will become strong enough that you will get ripped apart. So I don't really recommend it. Probably not a great idea. Okay, so here's a question. If no light can escape a black hole, how is it that we can see black holes? And this is becoming relevant now because we have actually gotten a picture of a black hole in the not too distant past. Here is in 2019, were released the first images ever taken of a black hole. And this isn't just a black hole in our neighborhood. This is a black hole in a distant galaxy, but it happens to be the biggest, most massive, super massive black hole that exists in the nearby universe, over 1 billion solar masses. And it happens to be one that is currently feeding, and which makes it so that it's bright and we can actually see what's going on. So just for some context here, look at the scale down here. This is 50 micro arc seconds. Remember, an arc second is a 1/60th of 1/60th of a degree. A micro arc second is 10 to the minus 6 arc seconds. It is 1/millionth of an arc second. 50 of those is a tiny unit of angular measurement. And this spot down here is the beam size. It's sort of the resolution of this picture. And everything about this picture is amazing. How it was taken using the Whole Earth Telescope. So these are radio telescopes that are positioned all around the Earth to give you the effective resolution, basically, of the entire Earth. And that's how you can get resolution small enough that you can actually pick out details of the black hole itself. What you're seeing here is also spectacular. I've posted a couple of videos down below explaining how this image was taken and made, and also what it is that you're looking at. What you're seeing is an accretion disk around this black hole where the objects, where the gas has been heated up a lot. And you're actually seeing both the front side of that disk and the back side of this disk as the light that's very near this supermassive black hole gets bent around in extreme angles. It's fascinating why you see this donut. The central thing is kind of the black hole, and you are kind of seeing an accretion disk, but it's not like you're seeing this face on. It's probably at some angle, but you're seeing both the front side and the back side simultaneously. It's fascinating and very cool. So take a look at those images and those videos in the supplemental material. Okay, but this tells you how it is that you can actually observe a black hole. If you've got a black hole sitting there in space, it's not emitting any light, and you can't really see it. But if you happen to have a black hole that's in a binary system with something, then that binary star can dump matter onto the black hole. Or if you happen to have a black hole that's that's near a lot of gas and dust, that gas and dust can fall onto that black hole. When that happens, it often settles onto an accretion disk, and that accretion disk gets very, very hot. Frictional forces within this accretion disk both cause this disk to be extremely hot, and also cause this gas to slowly spiral into the black hole. The misconception about black hole sucking usually comes from this picture where you've got gas spiraling inwards towards the black hole itself. But that only happens because of the frictional forces within the disk itself. And that disk can get really hot, so hot that it's actually glowing in the X-rays. And we see these binary systems out there. Here's one of them. Cygnus X1, the brightest X-ray source in the constellation Cygnus, is right here. And we think that's a black hole. Why do we think it's a black hole? Well, a couple of reasons. One is it flickers on very short time scales, like 0.01 seconds. Again, things can't change in brightness on a time scale that's faster than the light crossing time of them. They can't physically change that fast. And so that sets an upper limit to the size of this thing at about 3,000 kilometers. So this thing cannot be a normal star. But why do we think it's a black hole? Well, we know it's got a companion there. It is in a binary system with a B0 supergiant. This is a very hot, very massive star, and we can measure the spectroscopic changes in its Doppler effect due to the Doppler effect. We can watch this star wobble back and forth, and we can infer the mass of the thing that it's orbiting. And the thing that it's orbiting, we think, is about 7 solar masses. And so you cannot be this small and that massive and be anything other than a black hole. And so we think that this is a black hole here in the Cygnus constellation. Okay, we'll come back in the next video and talk about another way that we can actually observe black holes due to the things that they're emitting other than photons. Stay tuned for that.